All right, so good morning. We'd like to go ahead and welcome you to the 2019 SIAM Computational Science and Engineering Conference. I'm Suzanne Shontz, and I have my co-chairs up here for the conference. We have Jeff Hinninger. Go ahead and wave, Jeff. So Jeff is from Lawrence Livermore National Laboratory, and then we have Luke Olson from University of Illinois at Urbana-Champaign. So the three of us are co-chairs for this year's conference. We also want to say thanks to our organizing committee, and you can see everyone's pictures up there. We have Kate Evans from Oak Ridge National Lab, Hans Johansson from Lawrence Berkeley National Laboratory, Matt Nepley from University of Buffalo, Tammy Kolda from Sandia National Lab, Allison Marsden from Stanford University, Marie Ragnes from Simula Research Laboratory in Norway, Rob Scheikel, University of Heidelberg in Germany, Andrea Walther from Paderborn University in Germany, Stefan Wild from Argonne National Lab, Becca Willett from University of Chicago, and then Ryo Yokota from Tokyo Institute of Technology in Japan. And we want to thank them for all of their hard work. They worked a lot on different events and putting things together with us. On behalf of the co-chairs and the organizing committee, again, thanks for joining us here and participating in CSE19. Okay. We also want to thank our conference sponsors. So we have the Department of Energy, Office of Advanced Science Computing Research has supported the conference, so thanks to them. And then the U.S. National Science Foundation supported both the conference and the workshop celebrating diversity. Again, we want to thank the National Science Foundation. We also have several industrial and academic sponsors, and these are in no particular order. On the industry side, we have Intel, Julia Computing, AMD, Paratools, and MathWorks. Those are the industrial sponsors. And on the academic side, we have from University of Maryland the Applied Mathematics and Statistics and Scientific Computation program. From University of Illinois at Urbana-Champaign, the Computational Science and Engineering program. From Michigan State, they have Computational Mathematics, Science, and Engineering program. And then the University of Michigan Institute for Computation, Discovery, and Engineering. So let's give a round of applause to all of our conference sponsors. So we're very grateful for all of their support. All right, so some announcements and housekeeping notes here today. First of all, we are showing you the link to the online program. There is also a mobile app for the event. If you elected to receive it, you would have received your printed program in your conference bag, although some people, of course, opted out of that. Note that the printed program was, of course, correct at the time of printing, but there's been several changes since then. So we always encourage you to look at the online program. It's always going to be the most up-to-date with rooms and talk titles and speakers and things like that. And it does get updated every roughly 60 to 70 minutes. So note that's where you'll go to look for any changes. Okay. All right. Everybody's always interested in knowing what's the Wi-Fi network and password, so this is the information you will need. Note there's also an internet cafe that's available in the ballroom foyer during the registration hours, so that's another way to access the internet. Okay. In regards to recording, both the invited speakers and some MiniSymposia are going to be recorded, and they're going to be posted online after the conference concludes. And the archive material you can find under SIAM Presents on the conference homepage. Okay. All right. Note that book displays and internet cafe that we talked about and coffee breaks, these are going to be located in the ballroom foyer, so just outside of here. You can't get lost. We know this is a big space and it's a big conference, but look for the red poster boards that'll guide you to the SIAM meeting rooms. All right. We also want to make a note that the session chairs should review the session chair guidelines that SIAM sent to you and make sure to follow them very closely. All right. And make sure everybody in your session is sort of complying with things like that. So in particular, just one note there is that you should always be bringing your laptops to the session. SIAM does not provide laptops for you to use for your talks. Okay. All right. A note about drink tickets. So 2 complimentary drink tickets are provided along with your registration packet. After they've been used, you can purchase wine and beer at the events. And these drink tickets, they were to be used at the welcome reception, and also the 2 poster sessions that are coming up on Tuesday and Wednesday. Okay. All right, something new this year is we have some lounge seating that will be available Wednesday to Friday. This is after the career fair ends. The career fair is on Tuesday. So this is going to be in ballroom 100A, so right next door to us. This can be a good place to meet up with folks or conduct maybe a small group meeting, that sort of thing. All right, but that'll be available Wednesday to Friday. All right, there's also some concessions that are going to be on sale next to the registration area today. My understanding is that they might be available later in the week, but it sort of depends on how sales are going today, or at least early in the week. And note that, as an example, we do have some events that are scheduled over lunchtime some of the days. Sometimes food is provided, sometimes not. So, for example, today there's a early career panel. If you signed up for that, there is lunch provided for the students. However, if you're going to the funding panel, there isn't lunch, and that's a meeting that's occurring mostly during the lunch break. So the concessions would be a good way to be able to grab some lunch and also stay around for the funding panel. Okay? All right, so some important changes to meeting rooms, and these are for big events. So again, the lunch hour sessions today. One is our funding panel. It's called Future Directions of Research Funding Programs. That has been moved to the conference theater. And the early career panel has been moved to room 111A. And the reason for that is just due to anticipated sizes at those two events. It was necessary to switch them around. Okay? So these are the correct rooms for those two events. So please make note if you plan on going to one of those. We also have a note about the resume doctor. This is delayed until 3:30 today, so it will run from 3:30 to 5:30. The reason for the delay is just due to flight delays of the people involved in the event. Okay, and we want to highlight a few additional sessions of note from today. Michael Ferris will be giving a plenary talk this morning after we finished with our welcome remarks here. His talk will be on using optimization to model renewable electricity. This afternoon we have a plenary talk by Carola Bibiane-Schonlieb, and it's on deep learning for inverse problems. So those talks should be of interest to you. We also have a diversity panel tonight. This is new for us as well. This will run from 6 to 7:15 in the conference theater, and it's on strategies for promoting diversity and inclusion within our profession. So I encourage you to attend that as well. And lastly, I'm going to put up the list of featured mini-symposia. I'm not going to read them all to you, but these were basically mini-symposia that the organizing committee invited to be organized here at SIAM CSE, and we tried to have at least one in each of the conference themes. So those should be of interest to a large audience as well. All right, so with that, we conclude our welcome remarks. And I'm going to go ahead and introduce our first plenary speaker for today. So it's my pleasure to introduce Professor Michael Ferris to you this morning. He's the Stephen C. Kleene Professor in Computer Science at the University of Wisconsin-Madison, where he also holds courtesy appointments in mathematics and industrial and systems engineering. Also at the University of Wisconsin-Madison, he's the director of the Data Sciences Hub at the Wisconsin Institute for Discovery, and he recently was the optimization theme leader there. Dr. Ferris received his PhD in 1989 from the University of Cambridge, and his research is concerned with algorithmic and interface development for large-scale problems in mathematical programming. This includes links to GAMS and ample modeling languages, and general-purpose software he's developed, for example, PATH, NLPC, and EMP software. And he's worked a lot, not just on optimization and complementary algorithms, but also on applications including cancer treatment planning, energy modeling, video-on-demand delivery, and other topics. Dr. Ferris is a SIAM Fellow, also a Fellow of Informs. He's received the Beal Orchard Hayes Prize from the Mathematical Programming Society. He's a past recipient of the NSF Presidential Young Investigator Award, and he's received a Guggenheim Fellowship. Michael serves on the editorial boards of Mathematical Programming, Transactions on Mathematical Software, and Optimization Methods in Software. And this morning his talk will be called Modeling 100% Renewable Electricity. So please help me welcome Dr. Ferris.
Thank you very much.
Red button. Might have to press it again. Okay, it says it's on yours. Why don't you see if it wakes up? Okay.
There we go. Thank you very much. So I'd like to thank the organizers for inviting me to come to give a presentation here and for the kind introduction. And thank you all for coming at this early time in the morning. The work that I'm going to present is joint work with Andy Philpott, who's at the University of Auckland in New Zealand, and the pertinence of his location will become obvious, I hope, as I go on through this talk. The talk is about planning problems for renewable electricity generation, and I'm going to talk about the underlying trade-offs that arise in those problems. We'll formulate some models, some mathematical optimization models, and the intention of these models is to advise government policy. I will tell you a little bit about how we think about uncertainty in these problems and how we represent decisions that are being made in our plans. Okay, so underlying our system, there's an engineering problem. The engineering problem is a problem about electricity, and there's physics associated with the electricity. We can think about on the left of this slide, the generators are actually controlled by certain mathematical equations. Each of them have different nuances depending upon the type of generator. The point of the engineering a problem is to deliver electricity from those generation perspective over to the loads locations, and the supply is actually variable over time. There are physical engineering constraints. Those engineering constraints relate to the transmission lines, and so I depict on the picture some transmission line capability that is actually coupled in some linear or nonlinear equations to the generation specificity and also the specification of the demand. So underlying this, we have an engineering problem about getting electricity, generating it, and getting it from where it's at to where it's needed. Now we want to do this, the engineers want to do this reliably, so there are constraints that deal with uncertainties, and uncertainties can arise in lots of different applications and in lots of different ways, and I'll detail that later. And yet what we want to do is under some assumption of robustness, so we don't want the lights going off frequently within our system. Under some assumption of robustness, we want to deliver this at minimum cost. So there's a trade-off between the economic system and the engineering system. And finally, this talk is about those smokestacks, those dirty little things which are coming out of the top of the generators. And we're thinking about how we can actually add another constraint or think about environmental regulations, which we will postulate as constraints, and think about how that trade-off affects our minimum cost delivery of the engineering system. Okay, so just over a year ago, I decided to go on sabbatical leave to New Zealand. I was hoping to watch a bunch of cricket, a bunch of rugby, and go swimming. And then within 3 days of arriving there, the newly elected Prime Minister, Jacinda Ardern, came up with an agreement that her Labour Party was going to go in with the Green Party with two major assumptions, or two major points to this agreement. This actually ruined all of my plans, and I spent the rest of the time working on this problem. And so the first thing was that she made a request to the Climate Commission of New Zealand to plan. So thinking about planning to transition to a 100% renewable system in electricity. And then, as all politicians are wont to do, there were a couple of caveats that they made to this discussion. And one of them was that while renewable energy includes geothermal, which while it generates carbon emissions, there's lots of geothermal in New Zealand, so we're going to count that as renewable. And there was the other caveat that this was going to happen in a normal hydrological year, whatever that means. And so hopefully in the purpose of this talk, I'll at least explain some of those things. The second thing was an investment planning problem. So she was interested in an investment planning problem, and the idea was to spur, using 100 million of government investment, a green investment fund, to spur private investment of about $1 billion New Zealand dollars into carbon intensive, low carbon industries. So this is the problem, and what I hope to talk to you about today are models that will hopefully illuminate this discussion and tell us about the what and maybe about the how we could actually do this. So 2035 is what she was talking about. What about 2035? There's data uncertainty. The data uncertainty in this is that suppose you go away, as we did, and go away and ask 14 different experts, what is going to be the increase in demand of electricity between now, 2017 or 2018, it's actually 2019 now, so the work was done slightly before this, but we did these estimates. 14 different experts came up with the 14 different orange estimates of demand. You can then go away and strut your optimization stuff, and you can get 14 different plans, optimal plans, based upon those 14 different projections for how you're going to invest in different technologies and deliver that electricity. Which one should we use? Well, my claim is that we should use none of those, but we should use mechanisms that essentially hedge against our uncertainty and take some portfolio of investments, that those investments are actually determined by those multiple futures, but an understanding of those multiple futures. And I'm going to use some techniques in stochastic programming to actually do that. Second thing is, we don't know the data for 2035. We can estimate that data. What does the question mean? What does fully renewable mean? Before I talk to you about that, I'd like to first of all explain the picture on the bottom. So the context that we were doing this in was New Zealand. You probably all know that New Zealand is made up of two islands. There's the node S, which is the South Island. This is the place you should go if you're a tourist. It's really nice, very green and hunky-dory. There's the Cook Strait, a bunch of water between the South Island and the North Island. And unfortunately, the North Island is where most of the people are. About 40% of the people live in Auckland. And all of the electricity, which is depicted, most of the electricity supply is in terms of a hydro electrical system, which is on the South Island. So you have to get the water, which is delivered from this South Island in this large hydro system, from the South Island to the North Island. So the node H, you could think about this as halfway. It actually refers to Hayward's power station, but it's across the strait. So the orange lines are simplified description of a transmission line network, and they correspond to the places where there is going to be most congestion. So there's congestion because they actually have to have lines which go under the water between the North and the South Island, and then there's some other lines problematic between the Haywards, or the halfway point, and the North Island. The other issue is that in the North Island, there is actually some of that dirty power. So there's a coal and a gas plant, which is at Huntly, and that's to some extent the interest in our renewable energy. Should we shut down those power plants? So going back to fully renewable, what does fully renewable mean? Does it mean the blue thing? And I will use blue throughout when I'm talking about shutting down plants, an action which shuts down plants to remove those plants so they cannot spew the stuff out. Okay. Or do we actually want to actually think about a constraint on our problem, which is the constraint of we want to control the greenhouse gas emissions. So the green constraint is actually the result that we would like is to reduce carbon emissions into the atmosphere. So 100% renewable, well, we know what that means. We want to get rid of these things. If we actually went 100% renewable, then closing down all of the dirty plants is the same as closing down all of the emissions. However, if we want to go somewhere towards that, then these things would be different, and maybe these things are different anyway. So that's the question I wanted to address first of all in this talk. The first point I want to make is because of uncertainty, closing down plants is not the same as reducing emissions. And so there are three pictures here, and the key point to understand is that hydro is like a huge battery. So we actually have a huge battery. If we store the water, then we can release the water at a later date, and that's like storing potential energy from one time to another. So hydro is like a big battery. Because of the uncertainty in inflows, there's a possibility that there's a really long dry winter. Because of the uncertainty in the inflows, another uncertainty as well as the demand, then it might be that we need to hedge. We need to, in the summer, maintain artificially high levels of water so that if, in the unlikely event that we get a dry winter, we actually have some way to reliably generate the electricity. So here in the three pictures, you have the picture on the left, which is full Huntley. We don't shut down any of the plants. The middle is we shut down the coal, and the far right-hand side for you is the picture when you've shut down all of the non-renewable technology. And you can actually see a frequency of water. So the y-axis is the amount of water which is stored across a whole bunch of simulation runs, across a whole bunch of different hydros, and we have a frequency plot. So you can see that on the far right, the amounts of water, the distribution of the water is heavily tailed towards the top. We're storing more water, and that's just in case we get a dry winter, and then we still have enough electricity when we have that dry winter to actually reduce it, to produce the electricity, even though the capacity of our coal and our gas is decreased dramatically. The problem is, if you store the water over the summer, you're not having that water available to generate electricity. And so what you do is you use your reduced dirty coal and gas over the summer to actually keep those levels artificially high. And so you use the reduced capacity more frequently and end up with more emissions. So this is the work of a bachelor's thesis out of New Zealand, Ben Fulton. The trade-off here is that we've actually burned more fuel to maintain a higher level of hedging, a higher level of water in our reservoirs, so that in the unlikely event that we actually see it later, we actually have enough water to generate electricity. And then if it's a wet winter, then we have too much, and so we actually have to spill some energy or spill some wind. So I've talked to you about uncertainty. I've talked to you about uncertainty in demand. The uncertainty occurs in lots of different time scales. So first of all, the uncertainty was in the demand or the technology changes. That level, the time scale of that is in the time scale of years. I've then just recently talked about inflows. So inflows across seasons, and those inflows occur across different seasons, so they're on a weekly scale. The uncertainty in the inflows can actually be predicted on a medium-term scale of weeks. The wind and the solar generation are short-term uncertainties. Typically, we can do good estimates of those at the half-hour time scale. And then furthermore, then there's random failures. So either the transmission line catches fire and breaks down, or there's a random breakdown in one of our generators. Those are random effects that occur at the second time. So we have to span the gamut, all from seconds to years, and so any model that we generate has to be built with multiple timescales. Even if we're talking about decisions at the yearly timescale, we need to model things that are occurring at much finer timescales. And we're making these trade-offs. The trade-offs are between uncertainty. We have to make trade-offs between investment costs at the timescales of years and operational costs, which are happening at the timescale of seconds. And we have to, our model is going to be educated by both of those extreme facets. We have to worry about regulations, and I told you I'm going to worry about environmental regulations. And again, I have to worry about security and robustness. It would be unfortunate if all of our electricity were to fail right now. We have a certain understanding of reliability in our electricity system that we need to make sure is satisfied. So I'm going to use a simplified. First of all, I'm going to tell you about the major idea, and I'm going to use a simplified two-stage stochastic optimization model. I'm going to think about capacity decisions, investment decisions, how much Z I am going to have of each of these different technologies, and that's going to cost me K of Z. So that's a first stage decision, invest. Okay, once I've made that investment, there's some random demand, D of omega. Omega occurs in all of those random futures we've thought about. And then I need to operate at a level Y, so that we have a constraint that Y of omega has to be less than or equal to Z. We can't use more than we have. And then with that assumption, then we have a cost associated with operating that. There's a problem. The problem is that we might not have invested, so we have this trade-off between investment and operation. We might not have invested enough, and the demand might have risen so much that we might have to do Q, which is a lost load. We might have to curtail some load, and that's measured by Q. And so what we'll do is we'll penalize any lost load at the value V. It's a penalizations problem. So we actually have a two-stage stochastic programming problem. We want to minimize the capital cost plus the expected operating cost in the future. So that's the black problem. That's the economic and engineering problem. You could put all of your engineering constraints into this set X, so you can have those physical constraints to do that. But then in addition to that, what I'm talking about are environmental constraints. So the red constraints in here are the constraints that Jacinda Ardern was thinking about imposing, and that is the amount or the capacity here of renewables or of non-renewables has to be less than or equal to 1 minus theta times the capacity of the renewables that we have in 2017. So we want to reduce that. As theta increases from 0 up to 1, we go from the operating as normal right to the free of all non-renewable system. So that's my environmental constraint, or one way of imposing that environmental constraint. So with that in mind, how does that work? So we can solve that model. And this picture over here shows you on the lower axis, it shows you the value of theta. So theta increases from 0, which is the business as usual, through about 50%, 0.5, all the way up to 1. And this tells you that the costs associated with actually solving that model and imposing this reduction in this case, in CO2 emissions. Okay, some things to point out. So I actually split out the costs into 4 different costs. I'd split out the costs into an investment cost. That's given by the blue lines here. And you can see that the investment cost is increasing rather rapidly. Then we have a maintenance cost once we have installed it, or if we keep some of the coal or the gas around, then we have to maintain that. And then the operating costs are how much it's costing us to actually operate those plants. And the last line, when we go to 100% renewable, you actually get this lost load. And so it's only when we drive all the way to 100% renewable, where we have all of the uncertainties of wind and solar and those things coming in, that sometimes we actually have to lose load, and there's a trade-off between the investment cost, which is already high, and that lost load. There are lots of models which try and say, how can we recover those blue costs from a market that is actually using the green costs to actually determine the prices. We actually price, typically in the American markets, at marginal prices, And so as we invest in more and more and more nice renewable, because we need to deal with the uncertainty, the marginal price goes down, and yet the investment cost goes up. And so there are lots of models which are about capital investment or capital market models that could be used in this context. I won't go into too many more details, but that's what is driving the underlying system. Okay, I was lying. So for the next 5 minutes, I'm going to tell you a few more details about my simplified model. It's not quite as simple as it was there. The ideas are the same. So the ideas here are, and I'm just going to explain the one model, and I'm going to tell you the highlighted parts. So the first part, which I'd like to tell you about, is to some extent the first stage decision variables are slightly more complicated. We have a whole bunch of different technologies. Each of those technologies can be invested in at a level X and maintained at a level Z. And once you maintain them at a level Z, you have different costs. Those are first stage decisions. We need to know how much we're going to install. I like to think that we have been fairly clever in thinking about another first stage decision. And that first stage decision is to try and capture the uncertainty at that medium time scale. So a first stage decision, an investment in your problem, is an investment in the capital and the technology, but we also claim that there's an investment in the level of the reservoir. So you make a first stage decision independent of whether it's going to, you might have some estimates of whether it's going to rain or not, but you make an independent investment in the level that you're going to set your reservoir at, and you might deviate from that very slightly, but that's going to be a first stage decision that you make before you operate. So over seasons, I'm going to know where the level of my reservoir is. So those are first stage decisions, and I think this is a nice way of incorporating uncertainties at different time scales into a model. Second thing is the second stage. Everything in the second stage in here are random costs. They're based upon a quite complex model of a load curve, and we model that using data. This T of B corresponds to different blocks of our load curve. And so you have peaking plants, and you have plants that are addressing with base load, so stuff which is always on and stuff which happens because everybody drives home and plugs in their electrical vehicles at the same time. So we can model things like the duck curve from the California electricity industry using some data within this thing, within these load blocks and T of B. The third thing, as I've already talked to you about, is shedding load. Shedding load occurs because we don't have enough installed capacity, and we do that at a penalty B. So we actually understand that if we don't install enough or we get some bad scenarios, then we might have some much. Third thing I want to think about is how we deal with the uncertainties at smaller time scales and the difference between wind and hydro. So wind and run-of-the-river hydro, so run-of-the-river, I can't control it. I just water in is water out. I generate electricity there. So then we actually have a constraint on here, which is a constraint on the capacity of the wind. That mu factor is going to depend upon the load block, and it's going to be demonstrated to be different across each of those load blocks. I just don't do a standard formulation, but frequently the wind doesn't blow in the peak period. That comes from historical data. And so we generate these scenarios or futures in these mu's based upon different data which corresponds to the capacity constraint. How fast can you generate the electricity? So that's a random effect which is at the half-hour scale. There's another effect which is the dry winter. And that's at a different time scale. You can think about it as an energy constraint, an integral constraint. And so we actually have to sum up over here. We take an average here. So it's some form of an integral. And then the uncertainty that occurs in this are uncertainties which are predictions of whether it's going to be a dry year or a wet year or a nasty year or a good year. Okay, and so we measure both of those, and both of those things are captured as different types of constraints, and in a planning model, they're associated with this. Does it work? Well, I'm an optimizer, and so if I impose the constraint that we actually want to reduce the CO2 emissions, if I manage to solve that problem, I have enough technology or enough ability to build new technology, yes, it works. We can drive the CO2 emissions with a CO2 constraint down to 0. Hunky-dory. So it works. Bully-ho. Okay. That might not be the right constraint. So I talked to you right at the beginning that we actually have the constraints. So the green constraint is the CO2 emission constraint. So we can think about that CO2 emission constraint. But I said that you could actually think about it as a blue constraint. So instead of imposing a constraint about CO2 emissions, you could actually impose a constraint which says, shut down those coal and gas plants. That's the blue constraint. So you can actually impose an orange constraint as well, which is about how much energy you use. I'm not going to go into that in this talk. You could think about those constraints. Those are averaged or expectation constraints. You could think about those constraints as a mathematician as imposing them on an almost sure basis. So instead of imposing them in expectation, imposing them in every single scenario you ever see. We found that this didn't actually make a lot of difference in our runs, but that's part of the model that you could experiment with if you like. So if we do that, then instead of the green constraint, which goes down, that green constraint is now augmented with the blue, the capacity reduction, and the orange line, which is the orange line is how much emissions do we get if we do overall energy reductions. So we actually operate the things and reduce the non-renewable energy that we're using down to 0. So the green works hunky-dorily. We already saw that. The problem is that they've changed the rules. So if you change the rules and say that geothermal and carbon capture with storage, these nice green technologies that capture the carbon as it comes out and then stores it under the ground, if you say that those are now renewable technologies, then they still emit carbon. And so we can do this, the blue with the blue constraint or the orange constraint, but the net effect is that you actually just get a fairly modest reduction in the CO2 emissions, and not the emission to 0 that you would actually like if that's what your problem is. So be careful for what you want or how you do it. If you impose the constraint explicitly, so in the optimization you model what you want to do explicitly, you can do it. If you model it by a surrogate, by an action, closing down plants, for example, then you might not get the desired effect that you're after. Okay. So what technologies do we actually invest in? So if we solve those problems, so if I just do the capacity reduction, the easy place where we're just closing down plants, hunky-dory. You end up with a lot of gray. The gray is a lot of wind, and you see at the bottom of these pictures you have some red and some green. That's OCGT and CCGT and some other non-renewable technologies. Those are squeezed out, but geothermal is left in, and CCS, the SIAM stuff, also comes in as we drive towards 100% renewable. But the overall capacity, the overall installed capacity is fairly constant, so we don't have to have much more redundant capacity because these are fairly reliable things. But it didn't reduce the CO2 because geothermal and CCS still are big emitters of that. So you can do it with those constraints. The model tells you that this is fairly efficient in terms of capacity. If you actually want to impose the green constraints and drive CO2 emissions down to 0, then the capacity mix becomes much more of a rich portfolio. So you end up with lots of different types of batteries. There are batteries, we split batteries into slow, medium, and fast batteries. So different technologies that all of you are inventing are very effective at dealing at higher cost with delivering electricity more quickly. And as you see, as we drive to 100% renewables, we have some big increase in wind. We finally have some penetration of solar at high levels of renewable or decrease in renewable, 99% or 100%, and we actually impose these batteries. All of this is hunky-dory, except for you see that the capacity that I have to install actually goes up, and this is now becoming expensive because you have to install more capacity. How much does it cost? Well, So we have a constraint. We're all mathematicians. We have an optimization problem with a constraint in it. We can put a Lagrange multiplier on that constraint. This is called the carbon price. And then we can take that carbon price and we can take that constraint and lift it up into the objective function. And instead of parametrically changing the constraint, the right-hand side of the constraint, we can parametrically change the carbon price. So now on the bottom of this graph, I have the carbon price. Okay, so this carbon price is in dollars per megawatt. And this is hunky-dory. This picture should look the same as the other picture. That's what the theory says. Well, the problem is that the actual multiplier and the constraint, they are related directly, but the actual functional relationship is not good. I don't know what the function is which represents the multiplier corresponding to the right-hand side constraint. But the corresponding have the same picture, and we end up with generating things. The news is good. The news is good because actually what the people in politics will say, well, a carbon price of about 50, which is about the fourth graph, is actually reasonable. But if you want to go to 100% renewable, 100% renewable doesn't occur until you set the carbon price to 400. And the politicians will throw their arms up in horror and say, well, this is not possible. So the use of the Lagrange multiplier within our models is actually a useful policy instrument to understand exactly how these models can be used in a policy environment. The underlying models can actually provide value and also understand what technologies are useful and what technologies aren't. Some of my other colleagues would say, let's think about this slightly different. Let's not put the constraint in, but let's think about a chance constraint. If we think about a chance constraint, remember that they said we need it to be 100% renewable in a normal hydrological year. That's what the policy said in the document. 100% renewable in a normal year. So what does that mean? So one way we could think about it is you look at 50% of the years, and the lower 50%, you need to have 0 emissions. And then the other 50%, you couldn't care less. So the probability that you satisfy the constraint has to be bigger than or equal to 50%. Chance constraints. Super duper. We know how to do that. Integer programming will do that. We'll solve that. We come up with this distribution. So this is the distribution that, for one interpretation of what they mean by a normal hydrological year, actually gets a solution, and this is the technologies that you actually build. Unfortunately, compared to the 99% renewable case, this chance constraint involves a 60% cost increase, a 60% increase in emissions, and a 20% increase in cost, so it's inefficient compared to the 99% renewable case. But if this is so the advice to the Climate Commission is that this is not necessarily a good way of modeling it or thinking about how to model problems. Another thing that people might want to do is think about expectation. I talked about first stage and expected or average cost. But often in industry, industry is risk averse, and so they're worried not about the actual average cost, but they're worried about big, expensive costs which come out in the tails of our distribution. So we can model that using a different risk measure, and here we choose to use a sum of expected value and CVAR, conditional value and the risk, and I show you that the mix here of technologies changes as the risk aversion of the risk aversion of the people who are actually employing this changes too. So we essentially replace wind, significant wind, which is at the risk neutral, the expected value case, we replace that with CCS and some battery technology as we go more and more risk averse. So I can discuss this with you offline if you want. How much does it cost? What's the bottom line? So the bottom line in here is that as we saw, if you do blue or orange and don't really worry about the emissions, then the cost is fairly constant. So there is some increase in cost, but that increase in cost is very constant. When we go without geothermal or CCS, we actually get a fairly steep increase. So the last 1% or maybe the last 5% of increases or decreases in non-renewable technology are expensive. So you can actually quantify for the planner the cost, the physical cost, and those numbers are then useful to see them raise their hands in horror, their eyebrows raise up, and wonder about how expensive this is. I'd like to think about whether this is a good idea. So is this a good idea? Well, let's look at New Zealand. New Zealand, on an average year, emits 80 million tons of CO2 equivalent. So of that CO2 equivalent, about 45 million tons comes from the agricultural sector. That's not part of our problem. Somebody else has said, well, you can't touch that. Agriculture is too important to New Zealand, too important to Wisconsin. You can't do that. You have to leave that alone. So we're left with this 30 million tons, which is the stuff that we can think about, instead of the 80 million tons. Well, actually, we don't even have the 30 million tons, because the 30 million tons are about fuel combustion, and of that fuel combustion, about 15 million tons of that come from cars. We can think about, and some of the models, the results that I've shown, have talked about electrification of that yellow area. So electrification of our vehicles moves the vehicles from fuel consumption into the little blue container at the bottom. So we can move some of that demand by electrification of vehicles into our blue thing, and then it does become part of our problem. And the results that I've shown here have been built based upon models like that. However, even within that 30 million, within that 4.5 million tons, which were in the blue area, even if you add a little bit of not electrification of vehicles, there's still petroleum refining and there's some other stuff. So you end up with 3 million tons in the electricity sector. 3 million tons out of 80 million tons. I'm solving the problem. I have to get 100% rid of 100% of that 3 million tons, but forget about the other 77 million tons. That's not my problem. I don't think that is how we should be proceeding. And I think this is how the mathematics can actually be used. And I believe that in the future, we should be thinking about some general equilibrium or some methodology to take those consumers, which we're thinking about as consumers of electricity, but bring in other sectors to these models. So bring in sectors which are the agricultural sector, and those sectors are actually going to be combined with the sectors that we have for demand of electricity or demand for transformation by some mechanisms, taxing and so taxation and subsidies, which I talk about here as TC and TG, that actually transfer money, which we know about those money and those carbon prices. Those are those sigmas that I talked about 3 slides ago. And we use that trade-off to actually bring in more of the technology by combining models in a general equilibrium framework. This is work that we're embarking upon. We actually think about using financial contracts not only to mitigate different effects like that, but to mitigate effects of risk, which I touched on as well. So to conclude my talk, I'd like to just go over what I think I've told you and maybe reiterate what I'm trying to get you to take home with you. So I talked about 100% renewable electricity, and I talked about several interpretations. We could talk about capacity reduction, we could talk about CO2 reduction, we could talk about non-renewable energy reduction. I showed that those are not the same. And so if we are formulating models for use by people in an advisory or in a governmental role, we should make sure that they're setting the objective function to be the thing of interest, as opposed to choosing the action. Presupposing that shutting down plants will decrease electricity is not the same thing. I talked about uncertainty a lot, and I talked about uncertainty and modeling in an investment problem. I talked about approximations that we could do of uncertainty at different scales. Those were approximations, but I believe approximations of this nature are very relevant when we want to solve very large-scale problems. I showed you that if we change the rules and geothermal and CCS are considered renewable, then 100% renewable is very feasible. But if you change the rules or think about CO2 emissions, then 100% renewable in the New Zealand electricity system is actually needlessly expensive. And I ended up with thinking, trying to make you think about, are there mechanisms that we can draw in at an abatement price, so use the carbon price as an abatement price, can we draw in other sectors to enable us to solve these problems more effectively? The model I had was a two-stage model. I think this model can be extended in the future to be a multi-stage. We don't make investments now and never make investments again until 2035. These are stage investments. Multi-stage would be appropriate. We don't actually have one agent who is controlling every single generator in the United States or every single generator in New Zealand. These are actually market-based companies, and the modeling of competitive equilibrium, not only for sectors, but also within the energy sector, would actually be useful, and that's work that we intend to do or have already embarked upon, and I can give you pointers to papers on that if you like. I'd like to leave you with another trade-off. The other trade-off is a picture of New Zealand, blue skies and green fields, and the trade-off is you actually have some new sculptures on the horizon. Thank you very much. Yeah.
All right, so we have some time now for questions. You'll notice we have some microphones in each section. So please go to the microphone, maybe state your name, where you're from, and your question, and then Michael will answer it for you, okay?
Right, Sven Leifer from Argonne. Great talk, very important topic. I was slightly worried that the results that you were giving us, showing us on your slides, they were all accurate to 16 decimal places, and there were no error bars on them. So my question is this: the optimization problem, when you solve it, provides one answer. How certain are we about that answer? And is there a way of estimating that and providing, rather than providing a definite, this is the way how we distribute our renewable energy, is there a way of providing error bars that gives us more confidence that what you're predicting or what you're modeling is actually implementable?
Yes, we actually, so I didn't detail that, but even in the simulation runs that I showed for the Fulton experiment, so we actually did an a posteriori approximation where we actually implement our models and implement them in a simulation environment when they're imposed, and then you can actually run this with out of sample uncertainties that actually gives you exactly those distributions. So in the interest of time, and these were already complicated pictures, I didn't do that here, but yes, we have done that, and the details are actually in the accompanying paper.
Okay, let me jump in here and ask a question while people are maybe thinking of another question to ask. So I'm wondering if you could talk a little bit about the solution process. Your talk mostly focused on the modeling, which is very interesting. But with some of the stochastic programming, did you invent any new algorithms? Did you use sort of existing methods from stochastic programming, or is there anything you can say about that?
Yeah, so in terms of the solution of a lot of the socially optimum plans that most of the results that I've given in here, we're actually using technology which is standard linear programming technology for those problems. In terms of solving the models with equilibrium constraints that I alluded to at the end, the competitive equilibrium, then we actually had to augment the solution mechanism, and we looked at Danzig-Wolff decomposition methods within an equilibrium framework. So we looked at stochastic equilibrium problems and solutions such as Selke or extensions of path for those kind of contexts. So yes, we did do some of the work. Most of the work can be done using standard linear programming or mixed integer programming technology. As the size of the samples become more and more, or futures become more and more diverse, then these run into difficulty, and we looked at some new techniques for solving those as well.
Very interesting talk. My name is Peng Chen from UT Austin, Auden Institute. My question is, so there are so many uncertainties at different timescales. How do you model them at the first place?
So we modeled them using using scenarios. We actually took draws. We actually looked at historical data. So most of our data was based, for example, on water flow. So we were talking about dry winters. New Zealand keeps rainfall the values for centuries or a long period. So we actually had those distributions. For the use of wind, we actually had models of wind which were also stored, and so we actually generated uncertain data or our approximations of those scenarios, which I talked about, the muse and the news at different timescales. We used those based upon historical data to fit distributions of data, which we then used with random draws to actually populate our stochastic programming problems. So our stochastic programming problems were using standard form stochastic programs with lots of distributions. We use those as data. You could think about using distributionally robust optimization or maybe robust optimization techniques instead if you just have bounds on those distributions. We didn't do that. We used stochastic programming and formulated things with data.
Thank you.
Thank you very much for the talk. Ruslan Shadle in Clemson University. So you paint a very bleak picture. Like at high cost, we can get rid of those 3 tons out of 80, 3 million tons up to 80 million tons. And from your, this is more of a not mathematical question maybe, but from your experience working with policymakers and with people who actually tackle those problems, do you see a viable way to actually address the challenge of carbon emissions?
Yeah, thanks for the question. I wasn't trying to be pessimistic or anything. I think that we can get 99% renewable at cheap costs. I think there's a sweet spot there. And I think the sweet spot, so the first thing is that going to 95 or 99% renewable is viable at very good price. And so my last stuff about the 33 million tons, about the 8 million tons is saying that we could actually do more if we incorporate the other constraints. So it's not a bleak picture. I think that the technologies can actually do it as long as you couch the problem as doing 99 or 95% renewable. Because then it allows you some other technologies, some reliable technologies, CCS or whatever, which can deal with some peaks that the renewable energies can't deal with. And so I think that the story to take home is that we should be going after 99% renewable as opposed to 100% renewable, because this gives us a sweet spot, a trade-off between economic viability, which I think is doable at that stage, and the efficiencies that we want in terms of elimination of carbon dioxide, because we can do the rest of the carbon dioxide or even bigger things by incorporating some of the other things with biofuels, for example. In agriculture, we can actually give subsidies to that. It's an inefficient technology from an energy perspective, but by giving subsidy, we can actually double dip and deal with the emissions at the same time as we're dealing with the reduction in energy supply or the reliability. So I don't think it's a bleak picture. I think it's a good picture, and I thank you for your question.
Right, so in the interest of time, we'll take one more question, okay, and then we'll have to close the session. Okay, go ahead.
Hello, my name's Joseph Dawes. I'm from the University of Tennessee. My question is also slightly non-mathematical. It's one thing to convince a reviewer that the model you propose is good and that your solution is good. How does one go about convincing a parliament that your mathematical model is something that policy can actually be developed upon?
Hundreds and hundreds of runs.
Yeah.
So I think that the key point is that you build a model. That model is solvable efficiently using the technologies that we've generated. It provides outputs that are understandable to the policymaker. And we need to run it not in just the 5 or 6 or 100 simulations that I talked about now, but we need to do hundreds and hundreds of what-if scenarios. I typically get questions about, well, have you considered hydrogen, or have you considered concentrated solar? And all of those things, if they weren't in my picture, they weren't ever chosen by anything. But you can choose all of these different technologies as well. That's data. You need to put data into these models, but you need to instantiate that data into these models and build many more models and do many more runs to actually get some distributional effects that can actually then be averaged out by the policymaker to make appropriate effects. So I think the model is good, but the model has to be exercised and ran multiple times, and that's where practitioners and maybe not politicians, but their aides would be able to do that. Thank you very much.
All right, and let's thank Michael for that very nice talk. Thank you so much, Michael.